Okay, so it should be working now.
Okay, great. So you can start whenever you're ready.
Okay, so today we're gonna talk about multimodal models, in machine learning, and basically what multimodal models are models that take as inputs any sort of data that you can imagine. So it could be, for instance, image, text, sounds, but it could be anything that you can represent in a computer. The idea is that like you encode those inputs somehow using, for instance, a convolutional neural network in the case of images, or using any other statistical method that you can think about, or and then you represent it in this embedding space. And the idea is that like from this embedding space you can decode it to an output source, which can be an image, but it can also be a text, a sound, anything you can imagine. So for the simple case of the CNN, the convolutional neural network, you can imagine that you input in an image, you run the convolution in a network, and then you're gonna get like a vector that represents a label, which is a text. So a lot of things that I when I was preparing for this presentation, I noticed that in a lot of papers in multimodal, what you end up seeing is like, oh, we want to caption an image, we want to add subtitles to a video. So it's always like you input something and then you try to find a good architecture, you scramble things up, and then you get the output that you need. So that's why I thought like this little cartoon was a bit funny, because it seems that a lot of the time like there's like very complex architectures and that try to get the output that you want, but sometimes there is some reason behind it, but sometimes it feels a bit arbitrary. So like, wait, how do you draw a line? So going through this paper, like one of the very early principles of multimodal learning, like he says that like that the useful representation, so useful embedding, would be one that is a joint representation that captures like real world concepts of the data we're trying to represent. So that means that somehow an object an object that we're trying to represent, let's say a tree, can be captured in many different ways, but there's some sort of there's a way of representing it in an embedding space for each, like that particular object represents a tree, and then you can take another one, a chair, and then you can represent in the same space, and then you can take any of the inputs that you can capture from the chair and then represent it as being the concept of a chair. But of course, this concept gets a little bit difficult to. Philosophically, it's probably very difficult to say, like, when you think about a tree, what's a tree? Like, is it like a collection of different images of a tree, or is it like something that you describe? So all this type of problems is gonna come up like in machine learning. So just starting with like a simple warm up, like, so your conventional neural network is working on the left side, like it's taking an image of a dog. It's going through a series of convolution until it reaches a vector. And this vector, it has the same dimensions as a vocabulary. So the numbers that are in that vector are not inconsequential, meaning that they represent something that you can read from it and represent, that you can transform it and represent something else from that. So in this case, you can actually unpull and deconvolute the network to get back an image that represents like the areas where the particular dog is represented. So this is only possible because like that vector that is like very big and has a dimension of the dictionary has information that allows you to reconstruct the mask where the dog is, or you can or like, but you could also change the right part of the network for maybe you would like to capture the sound of the dog, you know, like so the barking of the dog. Perhaps you could also produce a similar sort of network where instead of like deconvoluting it into a data that has the representation of an image, you deconvolute it into a data format that has the representation of audio waves. So somehow like the different weights in that vector brings you back. So this is an example how it works. So when we start from this object here and then we unpull and then we reach this 14 by 14 layer, we will get something that's like figure B. And then you unpull it. So for each of these pixels, you draw a pixel here according to the place where it was in the unpulled layer. And then you go through like sequences of like unconvolution and depulling, and then you get back to the bicycle. So it's quite a powerful idea, I would say. But what is behind all that? I'm gonna cover a little bit of like how can we make sense of like this idea of like taking taking an object and then represent it in a space that then you can make some use of it. So in the deep learning book, there's a chapter that covers representation learning, and the main question of the chapter is like what makes one representation better than another. So in a sense, it's a very difficult question to answer because a representation is just as useful as what you're gonna use it for. So it's like it's some sort of like a circular definition because you cannot define a good representation until you define what you're gonna use it for. So and then you cannot know how you can build a good representation. So then it begs the question like, how can you go about building representations that can be useful for your task at hand? One way of interpreting representation learning is like as a pre-training, like so instead of starting from like an empty slack, you can train the network so that you can embed the image in or like the sound or anything, any data in your computer into an embedding space, and then after you can construct the whole network from when you can then optimize and get to perform the task that you want. So in this early paper presents the idea of like Boltzmann Boltzmann machine. So the idea is like if you take an audio input and then I encode it into a hidden unit, I will get this representation, and if I do the video, I get another representation. But even if they both represented, even if both hidden units have the same dimension, like somehow I cannot encode this in this hidden unit and expect that I'll get the same thing here. For the same reason, I cannot train a shallow bimodal restricted Boltzmann machine by just concatenating both inputs and then trying to get a shared representation, because at the end of the day, I'm gonna get that some parts of my shared representation represent just audio data, and some parts of my representation represent only video data. So somehow they're not entangled. They make the proposal that like I can then train my audio inputs to get the embedding of the data in some dimension, and I can embed my video input in another dimension, and then somehow I can train my deep belief network to get then a deep representation. So somehow you stacking different layers, you like removing all the information that is specific to that modality, and then what remains is like the core concept of that object. So the idea is to really like remove the intracorrelation in the modality. So the correlation exists is like, for instance, in an image you have a pixel next to another pixel, they're likely to be close together, but like maybe it doesn't mean like more abstractly that the way you represent a dog and a cat, like the idea of a pixel doesn't even exist like when you want to represent it. So like maybe you want to remove this idea of like of this intercorrelation between pixels or the intercorrelation in the audio waves, and then you want to represent it, and then you want to just take out the concept. So in going back to the deep learning book, like what a simple multimodal learning model is doing is you have an input X, and then you go from the input X to its representation on the space, and then you start from and then you take input Y, and then you represent, and then you project it into its own representation. And while you cannot compare both objects in the original space, you can map relationships between the representations because the representations are homomorphic. That means that like for each element in one space, I can map an element in another space, and not only that, I can trace relationships between. So I can if one point in this space, I can measure distance between one point in one space, and this will be equivalent to measuring another point in this space. So then in a sense, like I don't need, for instance, if I start with a description, let's say this is a text and this is images. So if I train the model with these 3 points here, and then now I would like to draw an image of this description here. Let's say the description of a dog. So an animal that has 4 legs and barks. So I would then represent this text in this space. And then because I know the relationship between all the other points in the space, I can then query for an equivalent point in this space based on the distance between the triangulation with the other points. And now I know how to decode this to the image space, and then I got the image of a dog. But then how do you know what's important and what's not? Like that's going back to the idea of like, how do you know if the representation is good or not? And then again, it has to do, and then the idea of like a representation is good if it's useful for the subsequent tasks that you want to do. Is the question about saliency. So like, to know which representations are good are the ones that kind of highlights the most salient features in the data. So if you start from the ground truth and then you train a model that only cares about mean squared error, you end up like producing images that don't have an ear, because a year a year in terms of an image, it represents like pixels very similar to the ones around the ear, and then it's only like a detail. It's like only some shadows like around this part. So if you're training a model that only has mean squared error, maybe it will like kind of blur the distinction between the ear and the surrounding area. But when you're training a generative adversarial network, you basically trying to teach the model that some features are more salient than others, and thus they are more like they represent the essence of the object more than others. Then what's important in a representation also is the idea of like the representation being distributed. So if you take a set of images and then you put them in groups and say this is a cat, this is a dog, this is a chair, this is a house. In a sense, you're right there doing a mapping between images and text, you know. But this is not useful because then if I show you an image of like an animal that let's say it's an elephant, and then where do you put it? You know, because it's not a cat, it's not a dog, it's not a house. But then if I have a distributed representation, like I can put images according to the components that form that concept. So instead of saying cats and dogs, I can say that has 4 legs, has a whisker, and then if I say if I present the image of elephants, like you might not be able to say that has whisker that barks, but at least you can say it has 4 legs. So then at least you know it's an animal. And it's not an inanimate. It's not an inanimate object, for instance. Of course, a representation is much more complex than that. But then in the end of the day, what the distributed representation allows you to do is to cut down complex representation to more simple representations that can be reused for training other tasks, and then away and then your model eventually finds it by somehow finding what's more salient between the two mappings, between the two inputs and the outputs. So it's so much it's so much going on. How do you decide on what's a good how to do good representations? Like so there's many ways of like there's many ways of regularizing your systems to try to make it to try to entangle, let's say, the input and the output. So you want to add restrictions to your model, and you're gonna get useful representation. So some ideas are that like a good representation might be the one that is smooth. So that like if you present different concepts, you will change smoothly from one to another. It's opposed to like one hot encoding, like so. And then it might be linear representations might be something that you care for. Also, you might want to have hierarchical representations because like then you can represent concepts of animals as like as a composition of different representations. And so on and so forth. And there are many other regularization techniques that you can think about. So here is the same idea again. Like this paper, like they want to build a generative model to be able to detect, to be able to label. So they wanna build a model that like they give you an image, and then you generate some text from So in this case, like they give you an image of a beach, and then you get this generated text, beach, sea, surf, strand, and this is what the user tagged the image, like in the real case. And here, the user didn't tag the image, but then the computer suggested this text. You can see like the tags are somehow more specific than the generated tag, than the suggested generated tag, and I think that it boils down to the fact that a human being knows the context behind the image, so it knows what it wants it to represent. Whereas the generated tags, it's being generated after you train the model based on the relationship between images and generated tags in the original data set. So of course you can only map like images to what it has seen before. So you cannot somehow like come up with like, in this case, like Sarah HT is probably the name of the photographer or the person who's in the picture. So the model would never be able to come up with that, like unless it had a lot of pictures of Sarah HC. On the other hand, because this is a generative model, like that is trained both on the image and the text, it can also give an input text, and then the model will give me some like images that are close in the representation space. So in this case, I get flower nature, green flowers. You got the two closest pictures to these descriptions as those two, and then so on and so forth. So the way the model works
So
is
maybe we can stop for a second.
Yeah.
Do you guys have any questions first? Let's go back and think about what the difference is between a Boltzmann machine, a restricted Boltzmann machine is from standard deep learning. So anyone want to elaborate on what those differences are? Yeah, go ahead.
One thing I know is quite different is that normal networks uses backpropagation to learn. Our Boltzmann machines, I don't know remember the exact name of the algorithm, but it's using representations to learn. So like you have the visible parameters, and then you learn the hidden parameters with that, and then
Observe
go-
them latent.
back and forth to learn the presentations.
Anyone else want to weigh on this difference? So, I mean, RVMs have been around for quite a long time. I think many of you know what an RVM is. Anyone is not familiar with an RVM? Yeah.
yeah, but I mean, it always comes up when you read about the topic of machine learning, but I sort of like get the representation like in what's described in Wikipedia, like the image, but I don't understand more deeply, or like what's the difference between that and a normal neural network. So because it seems to be the case that they were like in the beginning they were like only interested in Deep Boltzmann machines, and then suddenly nobody talks about this anymore, like or maybe this is too advanced now, like topic. So I don't know the difference very well.
Great. So this is a good point. I mean, in all the works that we try to do, I mean, a beginning scholar will say, oh, this particular algorithm is good for this data set. But then, when you look at another domain or another area, how do you decide whether the instances or algorithms that you have before will apply, right? So, for example, why aren't we using deep learning in these cases here that we're talking about? Is it because it doesn't fit, or is it because RBMs were a more primitive model, and only now that deep learning is more progressive, that we would actually redo this problem using just deep learning rather than a restricted Boltzmann machine or a deep Boltzmann machine? Right. And then likewise, why do Boltzmann machines turn up in certain applications and not others? So anyone have some input on that? Is it from a representation standpoint? Is it from a efficiency standpoint? Or is it because there are certain provisions that a Boltzmann machine can learn, or the deep network can learn that the other one cannot?
Yeah.
I think whenever you require a hierarchical representation in images, then they would use a Deep Boltzmann machine, because every layer is trained with, I think, I'm not sure about this, but every layer has a loss function to train on. And that's how they train, and then they would require the hierarchical representations to learn. It's good for images. And maybe for text it is not so. They would require some kind of other supervision, but for images you could learn segmentation and which parts are salient, which parts are not, with such algorithms, but not with.
I know that before they were like training layer by layer, because the computing power is not so good and the algorithms are not so good, and they didn't really believe in the backpropagation. That the backpropagation algorithm would be working, but in principle you could train a deep network layer by layer. Like it's a pre-training, because you can think of it as a pre-training. at least. So in a sense, like the Boltzmann machine, they always talk about undirected edges, which I don't know what it means.
I think it's as far as I know, the first these machines come out, it was due to the vanishing gradient problem. So this algorithm actually doesn't have that problem, and like it was when it first come out, it was like quite well. And the reason the edges are not directed is because the way this algorithm is learned is it tries to find the probabilistic distribution of one layer condition on the first layer, yeah. And then it goes forth and back to do this. So after you learn two of the layers, you just take your window to the next one. So then this window becomes the visible parameter, so it's like the first layer, and then the second one comes the second layer. So it's like goes forth and back throughout the whole network, and in the end you have this big representation of all parameters learned. And then one other reason it's good is because it's not labeled, right? So you can just throw any kind of data to it, and it does like pattern recognition through unsupervised learning. And then after you did that, you can just fine tune the whole network on some small labeled data set, and you'll get good results. But then I don't really know why they left it. Like it's like probably neural networks come better in the long race, and they were just abandoned.
So it's probability model. It's more.
I think I read intuitively somewhere that like a Boltzmann machine tries to see what kind of features generate the kind of input that's been input in, and then since a neural network is like a discriminatory network, it basically sees what kind of features are present in the image itself. So a Boltzmann machine basically says if this feature is wrong, then probably I need to change the kind of probability distribution so that like maybe given this kind of features, I generate a different kind of input to match what I've been given.
It's like a generator then?
Yeah, because it's a generative.
Yeah, correct.
But I don't know how this ties in with like why they use deep.
Yeah, I mean these two papers that I brought in the beginning, they were from very early, like 2011, 12. And I think at that time they were using more Deep Boltzmann machines than the more modern version of deep learning. But like I think the idea of probability makes more sense to me, because that's how they find the solution for this model anyway. They use a method called variational inference. That's also it's too high of a math for me now. But somehow they transform the probability distribution into this problem, and then they do like a sort of expectation maximization.
Other comments? So I think all of you guys have weighed in, and it does make a lot of sense, right? We use restricted Boltzmann machines mostly for fine tuning and unsupervised learning. So we want to learn a model from the data without supervision. Right? And then it can be used to pre-train a deep network model, right? And like Abhinav said, if deep Boltzmann machine typically has an observed layer and a latent layer, and then you're learning a representation for the latent layer using some loss function. So you stack them, you have hierarchical structure, right? So for some data that has hierarchical structure, for example, text with paragraph structure or something like that, or images with specific objects, maybe it makes more sense to be separately optimizing those rather than some single loss function overall.
Yeah.
Okay, so in all the readings and learnings that you do, you always want to ask yourself these types of meta questions. The easy thing to learn from any related work is, which model did they use for what problem? But then you should be asking yourself, sort of like in a GAN mode, right? Why didn't they use this model for that? Why wouldn't this work for that, right? Why is this the right choice, right? And sometimes the answer is, well, they just didn't do do it. Okay, so maybe it actually is a consequence. But sometimes if you read carefully or you analyze the data or you know the models, you'll be able to infer why something else was that way, right? Like I hinted many times in the reading group, a lot of your deep learning papers can't be trusted because the types of parameters they use for the network is good for this type of data set, meaning the quality and the quantity of data. It's the model architecture fits the data rather than anything else. Okay, so you have to be wary of that.
Yeah. So I mean, that's part of the reason why I brought this notion of no free lunch theorem. That I think is like a mathematical theorem, like that has been proven. Like I don't really know like the deep. I don't have a deep understanding of that, but I think the main idea is that like if you have a lot of problems and you have a lot of algorithms, some algorithms are going to work very well for this problem, and other algorithms are not going to work so well. But then if you get if you then throw the same algorithms in a different problem, it might be that algorithm A is going to be better than B, and then in other case, algorithm B is going to be better than A. So then at the end of the day, like if you're just doing brute force data mining, you're gonna eventually find a good algorithm for the data. Whether it's generalizable or not, then it might not be the case because you haven't really thought about you haven't thought about why you're using a given algorithm and a given regularization strategy, and what's the relationship between that and the underlying data generating process. So yeah, it's something that comes up sometimes also in the literature. They talk about this free lunch theorem, and I think it's relevant because a lot of the paper multimodal learning is like they have a clear idea of what they want to do, and sometimes like the architecture is so complex that I'm not sure if like they're doing that for a reason or if like they're just like trying to like make it work for their particular data.
The rule of publications is you need your publication to have enough novelty to get accepted. Okay, so that means in many cases, you know, you're using an architecture that's just enough to clear the novelty guidelines, right? So I have a criticism of lots of papers, especially from Asian scientists, you know, our groups included actually, where we sometimes introduce novelty for the sake of it. So that doesn't help, right? It doesn't help understanding. So in many cases, when you have a complex model architecture, you have to really strive very hard to explain why you need that level of math and sophistication in order to achieve something that maybe a simpler model will work. Right?
Yep. And then I'll finish my part of the talk bringing an application. So I work with spatial data sometimes because I'm interested in like urbanization and all sort of like dynamics that come in the urbanization process. And in a common activity that you do is like to classify regions of the city like according to some categories. So like more traditionally in geography, like you would classify a region as being touristic, as being residential, as being commercial. So if you simply took like, let's say, a satellite picture of this place, which is San Francisco, and then you look at this neighborhood and you look at this neighborhood and you look at this neighborhood, you would think like the two closer neighborhoods, they're more likely to be similar because they're close together. And then just looking from far, like you can't really make sense of an image like that. You can only see like a gridded pattern and an ocean and a big park. But then if you look at the description, like what people post about it, or like what they, or like if you look at like a travel guide, you'll see like this region is described as having banked apartments, office building, and region 1 and 2 they're described as having like gift shops, like tourist attractions. So at the end of the day, you'd probably agree that region 1 and region 2 are more similar because they serve like similar purpose, and also the yellow lines, they kind of show like connections between the two regions. So a lot of people go from region 1 to region 2, but less people go from region 2 to region 3. So like in a human geography sense, like region 1 and 2 are more similar than region 2 and 3, even though they're close apart. So in this case, like you would like, so in this case, like there's a lot of data about cities, you know, like there's satellite images, there's points of interest, there's like data from traffic flow, there's spatial graph data. So like, how do you like, so if you want to go about comparing different regions, maybe using it in a regression model, like let's say you want to predict the price of housing, like can I maybe like define a variable that captures like what's the essence of different neighborhoods. So that's why like they use the multimodal approach for like for learning an embedding space. And then a criticism that they make is like that traditional computer vision algorithms, they don't take into account the spatial autocorrelation that exists between in the geographical space. So like the idea is that like close things in space, they're similar, but closer things are even more similar. So they come up with like again like a quite complex architecture, like and then again like I can that's a little bit of my problem sometimes coming up with this literature is like this architecture makes sense. It's like no falsifiable. I cannot say, oh, this is not good, not bad. But then there's many other types of architecture you could think about that maybe could also produce a good embedding. But in this case, what they do is like they start with the satellite image here on top, and then they encode it using a denoiser autoencoder, and then they get a representation for the satellite image. And then for all the other data, they construct a graph where like each region is a node, and then regions are connected to each other either because of through the traffic data, so like taxi traffic data, and then they construct another graph that connects each region to each region according to if they're adjacent to one another. And then they run a convolution neural network using, like we learned last class, they use the skip-gram laws with negative sampling, then to produce a representation of this. And then third, they take the text data that represents flows between regions, and then they do similar. They use a reconstruction laws.
What's a flow matrix?
Flow matrix is like so each node in the graph is it's a region, and then the flow is like how many people go from region A to B. Like can be 50 people every day.
So in the literal sense of graph flow, like do they have transport information as well?
Yeah. The tax data and transport from taxi. Taxes.
The relevant pair graph in Slack.
And then they produce like two embeddings, one for image, one for graph, and then they will then concatenate both, and then they will run a multi-layer perceptron and produce a final embedding. And then the trick here about the multi-layer perceptron to avoid it having, because a lot of times when you're trying to embed something, like you concatenate everything, and then like half of the nodes will only look at one part of the embedding, and the other half will look at the other part of the embedding. But you want the things to be entangled. So the way they do is like they will sometimes trick. So they will put one image with the wrong graph, and then they will ask the network, do they both come from the same region or not? So that's how they entangle it. So then they get the embedding, and then what they use this embedding for, like, so there's a lot of applications.
The HI of global thing, right?
Yeah.
It is.
It's at the end of the day, it's a vector. It's like just a vector with numbers.
Oh, that's the output.
Yeah, this is the final output. Yeah. So they come up with a vector that represents like numbers, and then they show why it could be useful. So in one case, like here, you have a house pricing. So this is this is for Chicago, and this is for New York. And then a classical problem in economics is try to is trying to predict the house pricing. So like the most common regressions will just throw the raw features into the regression, and then they will try to predict the house. Like I've done this before, and then it doesn't work. It's like, or if you tried the Kaggle competition before, they had a Kaggle competition on house pricing. You get very bad results. And then there's other methods people have tried, like deep walking, node to back, things we have seen in the last lecture. And then in the case what they simply do is like they will regress housing pricing on the region encoder. That's what they produce, what I showed the previous slide. And then surprisingly, it has a very low root mean squared error. It performs the best for both New York and Chicago. So in a sense, like what's interesting is like, okay, you have a super complex network that will embed this in a latent space, but you never saw housing pricing before, you know. So somehow, like you're getting an encoder that captures you get an encoder that captures what's the spirits of that region, and that's relevant for like predicting housing prices. Because somehow we know, like if you go to a neighborhood and you see like it's very dangerous, it's like it has bad traffic, you know, like house price is gonna be bad there, you know. But then what happens if you just throw the raw features? It's probably like there's so much things that are very specific about the data that you're using, like satellite imagery. There's a lot of issues with cloud coverage. There's issues with like the pixel brightness, saturation. This might be relevant for the picture, you know, like for seeing the picture, but it doesn't really capture like doesn't really capture anything about the region itself, you know. So what we're trying to do with the previous architecture is just capture the essential. And then another application is like it's for querying databases, and then like let's say you also again like you show a satellite picture of an image, and then you ask for similar neighborhoods, and then the model will give you like the similar neighborhoods. So in this case, I'm showing is like a commercial district. So the model will suggest you the three closest in the embedding space, and then they turn out to be like commercial districts. Like you could also give some like points of interest, and then ask the database for similar regions, and then the model could give you like that. So it has applications in any search engine you can imagine that you're interested, like Google Maps and anything like that. So I think that's it from me. So I don't know if you have any questions, comments about this part. Otherwise, I will let my other colleagues continue.
Just one question. I just wonder if this sort of multimodal models, for example, is it possible to segmentize this geospatial data into maybe countries and their specific regions, like districts, sub-districts, that sort of stuff, like their street names. Have you ever come across any of this?
I didn't understand your question.
Oh, so maybe for example, an address has got like countries, states, maybe districts, their hierarchical parts. I wonder if this sort of application can be applied to that context, like segmentize into different regions.
I guess you could like use address as another input to your model. Like if you assume that address has some sort of like captures something about the reality of that region, like you could potentially use the address. Then it would enter as like a textual mode into the model.
I think it's quite interesting. Maybe I'll try to.
So I urge you all to look at this paper. I mean, it's on. I think I put it on Slack. The link.
Yeah, it's not very, the good thing is not very difficult compared to the other ones on Boltzmann machines. This one is quite straightforward.
Yeah, as soon as you run into variational math, many people have problems. I mean, the deep learning stuff is easy to pick up, but all the Bayesian and variational math is pretty hard. So yeah, that's a leg up on that. So I think it's interesting. This paper specifically says, if you look at page 2000, yeah, it's page 8 of the paper. That's page 2000. You see they do an ablation study. So I'll put the thing in Slack if you're not downloading it yourself. But it's very interesting to see that even though there are some of the other modes that they talk about that use all the data, that they don't do nearly as well. So you can see their method has much, much lower mean average error and root mean squared error score. It's the rightmost column in at least the Chicago setting works much better. And if you read the paper's conclusions, it does, also on page 2000, it tells you what they think is the reason why. Okay. So they say that the joint learning of all of the representations seems to be the big win. And like I've tried to tell many of you, it's important to do analysis. So this particular paper does a good job of that. It has a section of the evaluation of the latent space. So if you look at that section 4.6, they are actually looking at clusters of data points. This is the type of meso-analysis that I've always been telling many of you about. Okay, not to look at like the whole data set holistically, which you can do with metrics like accuracy and F1, but look at specific sections of the data set. So here they're talking about like downtown and Grant Park in Chicago, the suburban residential areas of Chicago, etc., and then trying to understand what it is that the model is actually learning in the latent space. Okay, so when you do your final year thesis or your your conference paper submissions, you always need to have this type of level of analysis. Okay, unless you're writing IR papers. I always made fun of IR papers. So yeah, information retrieval papers sometimes get away with no analysis. They just do metrics, which I can't stand. But that's just okay. So the IR community favors having lots of metrics for different data sets, and NLP favors having fewer data sets but more analysis. I tend to like the first one better because then I know what's going on. You guys want to talk about this paper much, or shall we hand it over to Yisong? No comments? It's a reading group. I should maybe call it discussion group, then maybe it'll be more noisy. Did you read the paper or scan it at least?
I'm not sure if I shared in advance because there were so many papers that I think I tried to share maybe like.
It's okay. I want you guys to start reading papers at this level. I mean, like if I give you a paper in 3 minutes, tell me the gist of the paper. Okay? Because that's the type of reading you should be doing. Mm-hmm. Right? If you have to go through all the methods and everything, and each paper takes you an hour to digest, you're too slow. You need to get to the core of the paper and how it connects with your relevant knowledge background very fast. Okay, so even in the reading group, I can ask you to read a paper, and in like 2 minutes, you should get some understanding of it. Like, where is the point that you want to really attack what you want to know from it? Okay, so to me, I rarely look at put too much analysis on the results because, again, like I told you guys all, every time you write a paper, the main results are always our method is better than the ones before. Okay, so why are you reading the results section, right? The important thing is like, why is it better? How much is it better? And what are the salient parts of the data or data set characteristics that would make it useful to apply this method? Because like I said, and Guilherme said, the no free lunch theorem basically is telling you there is no master algorithm, right, that's going to force everything to learn properly. Even in the neural network setting, you can learn all the parameters, but there are certain parameters or regularization strategies that are going to be better than others. And your job as a, somebody in the field is to figure out what recipe matches the right outcomes, right? Okay, so what did you get out of this paper? I mean, there's the region encoding architecture, which Guilherme showed us, the one that Alana was asking about a little bit. There's a GCN thrown in there for good measure, right? Because it's nice that we already covered graph-based models, so you know what the GCN is doing, right? So inherently in a multimodal model, you should probably see GCNs quite a lot.
Here they use the GCN a little bit like a denoising as well, autoencoder, but like with not with a little bit of a twist as well, like number 3, I think.
For the last point, for the MLP point, the only thing they train there is just like give pairs of hidden representations, and they either give it correct or not.
Yeah.
And that's the level, right? It's either
1 or 0. Yeah.
Nice.
Yeah, so this is also another example, because the earlier examples I showed, they all use the Boltzmann machine, but this is a classical deep learning architecture.
Let me ask you guys, all right, if you think about the types of data that are going into this study, there's graph data, there's mobility data, there's point of interest data, and image data. Before you carry out the experiments, which of these pieces of data is the least useful for predicting the real estate price? Which is the most important?
It's probably the prices themselves.
Okay, so the prices themselves, so that's like the adjacency, right? So being the prices themselves would have some adjacency criteria. So maybe that.
The image data at this level.
The image data, that's my guess. The image data is not very useful. Okay, but I don't know. We want people to validate that.
The degree matrix. I guess the nodes with high degree of centrality might be higher.
Okay, so degree centrality, something to do with flow or betweenness, that might serve a good marker. So that means like the mobility data would be pretty important, right?
But again, I would argue that it would work for Chicago and New York, right? I mean, they're very well structured with avenues and streets and everything. But if you take a upcoming city where there is mixed features everywhere, like it's not so well developed, then how would this work? And then the other features would matter. Here it doesn't even matter, the images don't matter. But there are parts of the city in the world, other cities where some features, some places look good and some places are just, then the image features would matter. But here it doesn't matter at all, I think.
Okay.
Two very well structured cities, New York and here. So
But it's because it's an aerial view, so can't really tell.
can't really tell,
Yeah.
yeah.
But maybe you could tell, let's say, from slums from another
Yeah.
part of metropolitan area. If let's say you go to India,
Yeah.
the city sometimes it's very visible from
You get
from
to
the
know
satellite
what's
data. Okay, those are good points. So this might work better for a very urban metropolitan area where there's not a lot of social economic differences.
differences. Yeah.
Any other things you wanted to point out about this paper? Okay, then let's first thank our first presenter. Okay, and I think Yisong is going to take over.
Okay.
So, yeah.
Should I stop sharing?
Yeah, you need to stop sharing so that Yisong can take over.
Yeah. Okay, cool.
Yisong, where are you? You're in California right now, right?
Yeah, I'm actually in Hayward Park. Do you know Hayward Park?
Hayward Park.
Somewhere. Hayward Park is a small city 10 miles from Stanford. Yeah.
Okay. So we'll just say you're in Stanford right now.
Yeah. Tomorrow I'm going to Stanford to meet one student of Professor Dendrovsky. Yeah. He might be helpful for our contextual lexical relation work. Yeah.
Okay, that's great.
Yeah. Yeah. Okay.
So thanks for staying up. I don't know what time it is.
Yeah. Yeah, it's fine. It's only 10 p.m. Yeah, it's still early. Yeah. Okay.
It's late in your city. So do you want to share your screen?
Yeah, sure. Yeah, I'm switching. Okay. Okay, cool. Yeah.
That's the problem.
Yeah. Yeah. Well, I think we all should receive this email. Yeah. Okay, I just start from my slides. Although ProfMin have appended my slides to Guilherme's slides. Yeah. Okay. But I will still
have to edit your slides a little bit on Hermes deck because those are in 16:9 and yours is I think 4:3. So the aspect ratio is a little off.
Yeah.
Okay. Anyways.
Yeah. So I'm still. Okay. Cool. Very cool. Yeah. Okay. I need a pointer. Yeah. Pointer. Yeah. Okay. Thank you guys. Yeah. And I'm Yisong. I'm a master student at Wing. And I want to thank Guilherme's presentation before. He talks more about the theoretical part of multimodal. And for me and Liangming, I think we both might talk more about the application parts of multimodal. So my research interest is in conversation system and recommender system. So I just by chance months ago read 2 papers on the intersection point between multimodal and my research interest, and I'm going to introduce them to you guys. And I think for me it is very exciting and interesting because these works are very, very new. They just published 1 year or 2 before, and they are very good work, and they integrates them integrates multimodal with dialogue system and the recommender system in a good manner. Okay, yeah. So let's come to our first paper. The first paper is titled "Knowledge-Aware Multimodal Dialogue Systems." The first author is Liang, and I will refer to her as Lizi. And this paper has won the best paper roundup in ACM Media 2018. Okay, so let's come to the motivation. So why do we need multimodal dialogue systems, right? So because they want to address a gap that previously all the existing dialogue system, they only utilize textual information, meaning that all the input information are text form, and all the utterances produced by the agents are also textual form. Li Zi and his collaborators argues it is not enough for full understanding of the dialogue. So how about you guys follow me and see this? And see this figure here. This figure is a conversation session. Okay, so the customer is a cat, right? The cat says hi. The agent responds, "Hi, what can I do for you?" The cat says, "Show some similar dresses in blue color." So here comes the problem. The customer cat proposed apparently sends an image. Then the system needs to understand what is the similar dresses according to this image, right? Meaning that the system must understand the image. And also the system, so the system has proposed some similar dresses. Then the cat says, "I like the second one, will it go well with the silver status?" So here means that the system not only understands the text, but also have some senses to match some fashion items for the users, right? So this is their motivation. So let's come to their problem definition, right? Their problem definition is almost identical to other works in dialogue system. Given the user utterances denoted by U sub 1 to U sub t, and also agents utterances before denoted by U sub 1 prime to U sub t minus 1 prime, they take all these previous utterances as inputs and output one generated one new agent's utterance. And here, the minor difference is that both user and agent utterance can be in two types of modality. The first modality is text, second is image. It is the only difference. Okay, so let's come to the framework overview of Li's paper. Yeah, we can see nothing special, right? Nothing special. Oh, no. So this is a very big framework, and don't panic. And there are total 3 innovation points, and I will elaborate them in the following slides. Okay. So the first innovation point is called the EI tree. E stands for exclusive, I stands for inclusive. And they use this EI tree model to extract features from for all the fashion items, including both text and image. So one may suggest that why don't you use a simple CNN to do such feature extraction? It's automatic. But the author argues that CNN can only capture generic features, but they want to capture some rich domain knowledge in specific domain. So let me give you one example. Let's say in the fashion domain, say that, okay, I want a pants, right? The fashion knowledge, the knowledge as pants, this knowledge has nothing to do with sleeves, right? Because pants is on your bottom clothes, right? But sleeves is for upper clothes. So this type of information are exclusive. And also there are some independent things. How about you guys follow me to look at the graph, right? So the graph, we can see that all the green line means they are inclusive of each other, meaning they can co-occur. However, the red lines means they cannot co-occur. And I zoom in this figure on the right-hand side. We can see that color and pattern knowledge can co-occur. However, let's say the animal and the big graphic, they cannot co-occur. So this type of independent information are also more fine-grained, and this type of fine-grained or constrained information, they argued, cannot be captured by CNN. So they use such EI tree. So how do they implement this idea? They implement it in this model, and I will elaborate it to you guys.
I didn't understand like the picture.
Okay.
You're saying that the color and pattern they can appear together, but then orange and pink cannot.
No, what he means is the color and pattern can both appear, but a selection of a value cannot be co-occurring with another selection. So you wouldn't say that you have a pink and red dress.
Okay.
You would say it's a multicolored dress. So those are the two things there,
okay.
Right? So you can co-occur color and pattern together. Like you could have a camouflage pink and red dress. Does that make sense? I think I've seen something like that before, although hideous as it is. But it's possible for those two things to occur, right?
Yeah.
Okay, cool. Thanks, Prof. Ming, for your explanation. Okay, so
there's the two things. There's the exclusive and the inclusive part. Exclusive means that, like all those red edges, right? That means only one of those things, only one slot value can occur, right? So a color can either be a pure black, or it could be multi. The pattern could be striped, or it could be big graphic, right? But a color and a pattern can both appear, right? So a dress or a shirt can have both of those qualities, right? Being applied equally.
Yeah, exactly. Okay. So let's see their model design. They use this model to implement the EI tree idea. So let's follow me to look at the left-hand side. Yeah. They use neural architecture to capture both textual and image information. On the upper side, they use LSTM models to capture this textual information and then get a hidden representation. And on the bottom side, they used this neural architecture to also get a hidden representation of the image. And they concatenate them together and fit into the EI tree. Okay, so as for the how can they transit from a root node to a leaf node, they model it as a multi-step reasoning path problem. So let's see this equation. On the left-hand side, the C0 stands for the root node, and the CNN stands for a leaf node. And the probability of transit from C0 to CNN, they have factorized this probability into the multiplication of n different steps, right? So they formalize it as a multi-step reasoning problem. So the F here is the concatenation of the both textual feature and image feature, and the big W sub EI is the weight matrix of the EI tree. And how they optimize this model? They use the ground truth leaf node to supervise learn this module by cross entropy loss. And here we can also see here's a ranking loss. You may wonder what function does the ranking loss has? The function is that they want to give a regularization between the image and the textual information. So let's see here. So here we can see the plus symbol, right? Meaning that these two matches with each other, means this text information match with this image, and they also have negative samples, and they use this style of ranking loss to better match the corresponding image and text. Okay, so here's the end of their first innovation point. Let's come to their second innovation point. And for me, I think it is the most intriguing and interesting innovation point in this paper, because they have incorporated an idea, I think they're very interesting for me, called fashion tips. Fashion tips generally happen when we guys, visit a real shop. We can consult with a real person, a shop assistant. Like say, we have bought a hoodie, an NUS hoodie on the left-hand side, and we may ask the shop assistant, what type of pants do you recommend that I should wear with this hoodie? And the shop assistant recommend with Levi's jeans, right? Levi's jeans, yeah. However, this type of fashion tips can be corralled or pre-processed, and anyway to be obtained for a data set, right? For, maybe you can see for any data sets, we can gain such fashion tips. But however, existing works cannot incorporate such fashion tips into the dialogue models. For example, if the whole training corpus or the conversation history do not contain such combination, they never co-occur before, the resultant dialogue agent has a very low chance to do a good job at such matching of the fashion tips, right? So they did such incorporation in a very efficient way. Their dialogue agent is based on a very famous framework called HRED. HRED stands for Hierarchical Recurrent Encoder Decoder. It is a very common practice for dialogue system. And their horcrux to do that is by customize the H sub T. Here, can you see the pointer, right? H sub t, which is the hidden representation passed from the previous utterance to the current utterance. They added by S. S is their domain knowledge. Yeah. So let's see here. Here's how they obtain the S. They use the memory network to obtain such S. So here, A and B are both memory network parameters, and the GI here is the representation of the knowledge entry. And how do they get such knowledge entry? They did it by the average of the representation. Say that the NUS hoodie has like say five appearances in the whole corpus, and they just obtain it by the existing pre-trained EI model, EI tree model. They just get the representation of all the NUS hoodie to this EI tree model and get their representation and average them up. Yeah, and here they obtain S, and they use this type of domain knowledge to enhance the performance of their dialogue agents, which has a sense of fashion tips. Okay.
So that means the memory network itself is like at training time.
I think okay. So the S here, this factor S here is pre-trained and they are fixed. But I think the memory network should be trained in an end-to-end fashion. Yeah, and they are trained. Yeah.
Right. So that means because the memory network is kind of like a memory, right? So like it's comprised of entries, right? So those entries are stored at training time and used at inference time. Is that it? Or does it populated at inference time?
Well, yeah. Well, I think the knowledge entries are obtained or stored before they are fixed, and the memory network should be trained. I think, yeah, their parameter is trainable. Yeah.
Okay.
Okay. Cool. Thank you.
I think so.
Okay. Yeah, I think based on the paper, the memory network is already trained with all of this. And yeah. During the online phase, it's being.
So in a sense, when the user is interacting with it, it already has like a memory bank of stuff. It's not like it initializes with nothing and then throughout the dialogue it stores the like certain things into the memory.
Yeah, I think it basically is incorporating the domain knowledge. It's not just used for the online dialogue. So it's not that the HRED is initialized empty, right? And then as the dialogue occurs, you're stuffing things into its memory. No, it already has some pre-trained knowledge. Yeah.
Right.
Because if you look at the paper, it's in section 3.2, incorporation of domain knowledge. So definitely it's already gotten quite a lot of trained information into it. They're using it to incorporate what Yisong said, which is the co-occurrence information about which types of fashion items occur with which other things, right? And then also looking at, I think the dialogue itself, right? What types of turns are happening in the dialogue that are usually discussed, right? So like say if you talk about tops, then probably what to ask about short or long sleeves, etc.
Yeah. Okay. Yeah. Let's resume. Okay. Okay. Let's come to their third innovation point. Is about reinforcement learning. They use reinforcement learning to fine-tune their dialogue system. So why bother use reinforcement learning? So let me give you a little bit background about that. The current state of the development of dialogue systems, they cannot function very well now, because sometimes they give some very non-informative responses, like okay, fine, thank you, something like that. The reason is that first, these things they're common, they frequently occur, and for me, I think the second reason is that these responses are safe. Maybe they can be less penalized in the training time. Okay, so talking about reinforcement learning, what is the first concept come to our mind? What is the first concept come to our mind? It's the reward function, right? It's the reward, yeah. So let's say, how can we give a reward to a dialogue system to guide it to train, right? I think generally speaking, and to the reward design is a quite heuristic and a pain in the neck, yeah, pain in the neck thing, yeah. According to the workshop in the Wisdom Conference, Professor Jian Yunye also talk about conversational recommendation. He says that current style of reinforcement learning will suffer a problem of the heuristic to design the reward, not quite automatic ones. Well, yeah, I think as for a task-oriented dialogue system, the reward should be given if the task can be accomplished, right? Yeah, for example, given a conversational search engine, a positive reward should be given when the agents successfully obtained the results of the user's query, right? Well, as for Li's paper, I'm not quite sure if it is a task-oriented dialogue system. I think it should be, but I found they only use the blue score as the reward function. So apparently, Liz did not specifically learn a strategy thing. They emphasize more on the language parts, emphasize more on the conversation coherence. For you guys, if you don't know blue score is originally used in the field of machine translation to measure the quality of machine translation. It measures the overlap between a source language and the target language. The more overlapping, the higher blue score is, right? So, sorry. So let's see this function here. The R is the reward function. Is calculated before between the one more utterance by the agents and the context, right? So what is the context? Context is the whole conversation history, including the user utterances, all user utterances, and all agent utterances, right? And they use the standard policy gradient method to do the
utterance in the embedded space.
Mm-hmm. Yeah. I think they are in. Well, yeah. Well. Okay. I think I need to check some details, but they use the blue score. I think maybe they should in a text form. Yeah. I'm not quite sure here. Yeah.
So I think they use the blue score for text, but then they use image similarity for the images as the reward.
Yeah, exactly. And here I only talk about the language part. Yeah.
It's really weird that she uses RL because it's like one step, right? Like usually for RL you calculate the whole rollout, but then this one is like every step you just
get one step and then yeah. I mean, it's more typically to see a rollout. They're still using the average, right? The difference between the average.
But then it's like one. I'm assuming it's just like a single step. It's like a single step rollout.
Yeah. TRL actually means.
What's the question?
The question was about how they're doing the learning. What loss function they're using for the policy gradient. So that's line 2, where the nabla is.
Oh, they go from 1 to 2?
No, I mean why they're doing the PRL. Part.
Like why are they using RL in the first place?
Oh.
Like why don't they use MMI or something?
MI?
Like mutual information for the consistency problem. I mean for the safe response from. Because like I think in translation or dialogue generation, there is also this problem of safe responses, and they use, instead of maximum likelihood, they use maximum mutual information. So yeah, I don't know why they use RL.
Yeah. Another sorry.
Yeah, I can hear you.
A very simple but efficient method to address this kind of problem is just to reduce the beam size. It is really efficient to reduce this kind of error, this kind of safe response errors. Because when your beam size is large, so in decoding, it is more easy for the models to give the high scores for these kind of safe responses because they are typically short and their frequency is high. So they will get a very high score if the decoding model is be able to see this kind of response. Because when your beam size is large, the model is able to see this kind of responses. Yeah, so in this case, just reduce the beam size, and then this kind of error will come. But it will introduce another kind of error, which is that your responses will not very the grammar is not very good.
Not so good.
Yeah. So do you guys all get that point about beam size that Liangming was talking about? No. Okay.
I'm not quite. Yeah.
I don't know what beam you're referring to.
Beam is the size of the number of hypotheses that you might be using for you generating the response.
Okay.
Right. So when you traverse a number of states, you keep a number of candidates open for realization. And so each time you go through a state, you let's say pick 5 things that you might want to say.
Okay.
Right? And then you go to the next state and you say, okay, from those 5 that I kept from last state, which ones do I want to pursue? So every time you do that, you generate more candidates, but because your beam size is limited to 5, you always keep the best 5, right? When we think about optimum decoding, it's always one best, right? You just, at the end, just choose the best one, right? If you have a beam size of 1, that means that the particular response that you chose was the best one for every time step. Right? But that's greedy, right? So many times if you have a suboptimal decoding, it's somewhere in the middle, but ultimately ends up to be the global best, you'll miss it if you do a beam size of 1, right? So the problem that Liangming was pointing out when you say your beam size is too large and it picks up all of these safe responses means that those safe responses are okay, but they're not the best for any particular response. But because they show up in every n best list, they become the best thing to do almost all the time, right? It's always good to say, yeah, I understand, whatever, good. But you know, in the end, do you actually know what you're talking about? And the answer is probably no. I was sort of paying lip attention to you, but I don't understand what you say, right? Maybe you do that to your girlfriends or boyfriends once in a while.
Actually, like in the, I didn't understand like how do they measure, what's the ground truth like in the dialogue?
So the ground truth, I think, is the actual dialogue that was emitted by that particular data set. Is that right?
Well, I think there is no ground truth. They just use the blue score to guide the policy.
I mean, there has to be a ground truth if there's a blue score, right? There must be some reference to operate on.
Well, I think the blue score is calculated between
what kind
the
of
patterns and the context.
It seems like such a complex setting that
it's a special data set by IBM. Like, it has the taxonomy and all that stuff also.
So they just have with similar dialogues like that.
So it's a multimodal dialogue data set. So they are basically exploiting the taxonomy that comes with the data set.
Okay, I didn't. So it's a very specific, like, so this data set contains a lot of
it contains everything that they.
A lot of this similar dialogue.
And the pictures and everything also.
Oh, okay.
For the safe response, is there any explicit like regularization technique so you can give penalty for giving such safe responses? Other than fine tuning using.
Yes. Remember I see. I don't remember what is the paper exactly, but I think I have seen a really simple trick, which is fine tune based on the frequency of the response. I mean, it just modify the process of beam search, and when it encounters a response like this kind of response, it just regularize it, reduce its scope in the randomness.
So something like underlying inverse mapping.
I'm not sure what they are based on, but the essential idea is based on the frequency it appears.
So yeah, if you look at the original paper, yeah, they do tell you a bit about the multimodal dialogue data set. I pasted the relevant part in Slack. They have 150 conversational dialogues between shoppers and sales agents. So they do have ground truth. It's from an e-commerce site.
But like the settings, like they start with the same sentences in the dialogue, and then they expect the model to generate the same dialogue, or like.
Yeah, so you can read it. Yes,
Yeah.
it would be blue score is not expecting you to create the exact same, but yeah, measure a degree of overlap. Like that. So I mean, for dialogue agents, yes, this is a big problem that Juan here pointing out is that you can always give a safe response, right? And that Liangming pointed out the frequency-based approach is a simple way to do it.
So, but what I mean is like if the dialogue if the dialogue goes a different way, like, but it still would make sense for a human, but like then the blue score would be very low, but the dialogue would still like, so then the model would, then you would classify the model as not so good.
Yeah, so we're going to see this again and again. For a lot of NLP applications and other like IR applications, there can be substitutable results that are just as good, right? So when you have subjective evaluation metrics, you usually need multiple gold standards. So you could say, okay, for this one dialogue, I'm going to simulate several people saying it differently. They collect different things. And you'll see this in recommendation systems. I think Eng Chan and Taka are going to cover that. But recommendation systems is also, well, how do you know whether it's a bad recommendation or a good one, right? So it's subjective. So you have to average it over lots of data.
Yeah, actually, that's why the beam size cannot be too small. Because that is why in the dialogue system, the beam size, we cannot set this as one. That is, we cannot find the best one. Probably we can choose the best five one. Probably there is one can match the one chosen in the data set. And also in the recommendation system, it's the same. In most cases, choose probably in the top 40 items, 40 tries. And if there is one match, as we said, it hits, the hit ratio is 1. That's the same.
So I think the other thing that someone else proposed also was the maximum mutual information objective instead of the standard one. So you take the standard likelihood and minus the probability of the sentence appearing in the first place, in all the corpora without any, like, not the conditional probability. So you take the conditional probability, so like t given s minus t. So
this is like a surprise metric, like how novel is this response compared to what's normally.
So that's the regularization factor.
Yeah, I mean, if you think about like other places where this comes up is like when you do annotation, right? There's often a kappa score that you calculate, right? And kappa is supposed to correct for random chance agreement. So this is sort of what Samson is saying. Mutual information is saying, what's the no-brainer chance that this response is going to show up? So when there's a common response that's always indicated, some of the time, you can subtract away that probability mass using this idea.
Kind of like normalization.
Yeah. Okay, Yisong, do you want to go ahead?
Yeah, sure. Okay. Seems our this slide has stirred up quite a lot of discussions. Let's move on to the experiment parts. They have distilled 3 research questions to guide their experiments. And actually, these 3 RQs corresponds to the 3 innovation parts I mentioned before. As for the sake of time, I suggest you guys to refer to their original papers, and directly we jump into our second paper. And it's now for me it's 10:40. As I want to leave more time for Liangming to present, and I will make it shorter.
Yeah, sure.
Okay, let's try to go ahead.
Yeah. Okay. Yeah. Second paper is titled Interpretable Fashion Matching with Rich Attributes by Dr. Sun Yang from Next Group. Next Group does not refer to the group next door. Next is the name of the group. Yeah, it's from the Next Group in NUS. Yeah. Okay. I'd like to first give some preliminary. Preliminary is called TAM. This framework is called TAM. The full name is the Tree Enhanced Embedding Model for Explainable Recommendation. Okay, so talk about explainable or interpretability. It has become a main issue in current advances in neural networks, right? So let's talk about the explainability in recommender system. Recommender systems, in short, it is going to give a score between a user and an item, right? The more similar or more matching this user and item are, the higher score they will receive, right? We have seen many useful models like collaborative filtering, factorization machine, and also the neural network version of these classic models. And also, and these neural network versions are pioneered by our Wing alumni, Dr. Xiangnan He. Yeah, but the question is that they're not quite interpretable. Yeah, and the author of the TAM paper, Dr. Xiang Wang, also introduced that recently, the higher performance a model can achieve, the less interpretability a model can maintain, right? So this work, TAM, can strike a good balance between the performance and the interpretability. So let's follow my pointer on the screen to look into this model. The interpretability mainly comes from this decision tree. We can see that there are many user attributes and item attributes, and they have trained a GBDT, means a cluster of decision trees, to form many paths. For example, on the right-hand side, we can see one sample path can be like age equals to 2025. He's a male, he loves soccer and tennis, and here it comes down to one leaf node, say this leaf node. And we can see that on this layer pointed by my red pointer now, this leaf node, each leaf node actually corresponded to a cross feature. And they use this cross feature to enhance the performance of the recommender. And later, after they have gained such cross features, they map them into one hidden representation, namely V sub 2, V sub 4, V sub 7, and that together with the user embedding P sub U and the item embedding Q sub I, they feed them into one attention nest, shadowed by blue, their attention nest, and they got the attention score, and they did the max or average pooling together, fit into here is a MLP multi-layer perception model to finally give a score between the user item and their attributes, right? So the interpretability part is achieved by the decision tree here, and the performance part is guaranteed by the neural architecture here, because the neural network somehow has a generalization ability, right? So here is a good balance, and I like this work a lot. And previously, I also tried to use this model for a NLP task, and this work is still under preparation, and we have some preliminary results. Yeah, and so the idea is to use the decision tree. For me, I think maybe decision tree is the most explainable machine learning method, because it's naturally explainable, right? From the root node to the leaf node, the path is the decision path. It's naturally explainable. Yeah. Okay. Given that we have understand this preliminary, it's very easy for us to understand this work. This work, the problem definition is spatial match. For me, I'm not an expert in this field, but in short, I can see that a fashion match is to model the interaction between item and item. However, for recommender system,
can you let speak for a minute?
I want to ask a question.
Okay.
Yeah. Oh, okay.
Last page.
Yeah. Okay. Yeah. Hi, Hengchang. Yeah.
I'm curious about the decision tree. Do you
mean how to build it, right?
In this paper, do you need to go through all the paths? Because there are lots of permutation.
Yeah. Okay. I think you raised a good question. You mean that when you use, say, the training corpus to form the decision tree, if we change some random seed, there are many types of decision tree, right? You mean, do we need to try many trees? Have I get your question right?
Yes. Yeah. Because for the results from decision tree, you need to then send there to the neural network or NLP, kind of like then compile or the ranking the results. I mean, it costs a lot if you go through all decision tree, and there are lots of combination.
Yeah. Okay. Thank you for your question. And I think if my memory about their paper is still precise, I think this type of questioning is achieved by the GBTT method. GBTT is a cluster of trees. I think according to their implementation, they use like 10 trees or 100 trees. Yeah. I think it is not quite expensive, because tree method, I think they are fast enough. They use the XGBoost library, and it's still fast enough to get 100 trees. I think for training time, it takes, according to my experience, if the depth of the tree is like 6, the training time can be like 1 minute. But as for the inference time, it's very fast. And then just randomly throw one user and throw one attribute, through one user and item their attributes, it can very quickly to generate 100 decision tree in the cluster of the GBTD. And I think the computation efforts in this part is not a problem. Whereas for this parts, maybe you are concerned with the computation load here, meaning the attention net. I think it makes sense, and but according to their implementation, they seem to use 100 trees, meaning that for each tree, they will certainly have some leaf node, right? So like say 100 trees, so they will obtain like 300 leaf nodes, and plus the user and item embedding, there are 302 embeddings to fit to the attention net. Yeah, I think maybe it's still tolerable. Yeah. Okay, clear, Hengchang?
Sample the path. Like that.
Okay. Thank you, Hengchang. Okay, so I think it's very important for me to introduce this work to you guys because I think this work is very important. Again, it's a balance, right? So let's say a balance between yin and yang, right? Yin and yang, right? Yin is the performance, yang is the interpretability. Yeah, so I think this work is a good balance. Okay, so let's come to this paper about the fashion match. Fashion match. They want to match some items, right? Here are some a dress. Here's a jeans and the shoes, right? I think for me, I'm not expert in the fashion match. I think they model the item interaction. Whereas for the recommender models the item user interaction. I think maybe it is the difference between the fashion match and the recommender part. And for this work by Dr. Xun Yang, he used the rich fashion attributes in the data set to enhance the performance of originally only the image information systems. Yeah. And here it comes to our framework overview. This framework is called AIC, Attribute-Based Interpretable Fashion Compatibility Framework, AIC model. In the AIC model, given that we are very familiar with the TAM work, the decision tree recommender work, we can very easily understand this work. So in this part, where I'm circling with my pointer, they are almost identical with the TAM model. And on the left-hand side, they use the image information, feed them into the CNN and get their hidden representation, and to get together to calculate their attention score and for the final prediction. They are not complex. Yeah, given we understand the preliminary, this work is not hard to understand. Here we can also see that they, in this whole model, they incorporate both the image modality and here maybe the attributes modality. Given that this model is not complex, I want to have some takeaways for you guys. Actually, this idea has been a surprise for me when I first read this paper because I think this idea is very good. It's about embedding compression. So let's say that we need to have a representation about all the edges in the tree, right? Let's say that we have, given this node, material equals to wool, right? So there are two decisions, either yes or either no here, right? So meaning that given an attribute space of size of A, we need 2 times A to represent all the edges. However, they made an innovation. They introduced another vector called SK. S stands for the decision, meaning that the AK here is still the attribute embedding, but the SK is the decision embedding only for yes or no. So the embedding space has reduced from the 2 times A to A plus 2, almost only half of the embedding size. So it can save match space and prevent overfitting. Okay, so let's come to their experiments. They also use three research questions to guide their experiments. I refer to you guys to their original paper for more details. So let's come to our key takeaways for my talk here. And so this is the last page of my slides. Preliminary. Previously, I only want to show you guys 2 papers I read before about multimodal. But later I find that they have one thing in common. The common thing is that they both use the tree model, right? They both use tree model. So we can witness a phenomenon that's the tree-based methods in multimodal. So this is a phenomenon. So let's have a review. In Lisa's paper, she used the EI tree to incorporate such fine-grained taxonomy-based attribute information. As for in Xin's paper, he used the decision tree to find the cross feature about the attributes. So for me, I think I'd like to share some of my understanding about the tree structure. they have pros and cons. The pros, first, as we introduced before, is quite explainable. And second, it is quite structural. So let's say we have thousands of attributes. We can just represent them in one tree if the tree has the depth of 10, right? Or in a cluster of GBTT tree, right? But they also have some disadvantage. I think the main disadvantage is the generalization ability. For example, so let's say if we want one cross feature, let's say in this work, we want one cross feature in the testing time. But if this cross feature has never been shown in the training set before, meaning that they cannot hit such cross feature, they cannot find them. So it's another kind of other vocabulary problem, yeah. So so I think there is still a balance, yeah. Given a model is explainable, it might suffer from the problem of generalization. Okay, so here it is the end of my talk, and thank you guys. Yeah. Okay, thank you.
Can I ask one question?
Yeah, sure. Go ahead, buddy. Yeah.
So actually, I didn't quite understand how EI tree is used in the first paper. Like for example, how is an EI tree different as compared to like a knowledge base, and how are features extracted from like an EI tree, for example?
So the EI tree was manually constructed.
Oh, okay.
Yeah, it wasn't automatically constructed. They had a domain expert create that particular taxonomy. Yeah, but it's that tree is then, because it's a computational resource now, it can be used to do the recommendation.
I understand EI tree isn't something that input to the model. So you use to compute the EI loss, something called EI loss. So there's like the rules, and then the output must conform to the rules of the EI tree, otherwise there'll be some losses. Am I correct?
But if it's used, sorry.
Go ahead.
But if it's used only for loss computation, then how does the model understand knowledge in this case? Like, wouldn't the knowledge, the domain knowledge, would not be transferred over to the model? It has to be somehow used. Like the text has to be somehow used in a way so that it understands like different products again, like the shirts and the shoes.
Yeah, so there's definitely alignment between the EI tree and the text. And then I guess the EI tree is used to tag the image data too. So that the image data that's being recommended has EI attributes assigned to it.
And that makes sense.
So like a dress would be coded as blue, solid blue long dress, for example. So those parts of the EI tree nodes are activated for that.
Yes, I understand.
But then like Huang was saying, you can do loss computation on that, right? You can say you recommended a dress that was green and long rather than a dress that was blue and long, right? Or a long, a blue dress that was short, right? So this would have different losses.
I understand. Thank you.
Okay, let's give a hand to Yisong for being in a completely different time zone and presenting the note. Okay.
Thank you guys. Yeah.
It's almost free, but we did start late because we had to fumble with Zoom. So Yisong, you're welcome to sign off, but we'll ask Liangming not to take a break after all, and to Zoom, pardon the pun, through the rest of the presentation. So we have to go back a couple slides. So I think learning slides before I inserted Yisong's one. There are a couple
Yeah, correct.
Hi, so are you can stop sharing screen? So that
Yeah, sure. Yeah, I'm going to operate that. Well, how can I operate that? Stop sharing. Yeah, stop share. Okay, there. Yeah, stop sharing.
I think you can
stop
still
video.
hear Liangming even though his microphone isn't on because we're using the big mic. So Liangming, you can just project your voice a little bit towards the microphone. Yeah, you can turn off your mic. Just use the one that's on the table.
Oh, yeah, sure.
I think we can hear. So we'll try to go for about 10 to 15 minutes.
Yeah, okay. Yeah, I can do that. So okay. I will cover the topic of image to text generation because my research topic is about generation, so it's suitable for me to do this topic. And my introduction is more on the conceptual level. So yeah, it is suitable to be the last one to present because they assume that you are tired. So I want to cover some much complex models. Yeah. So first, what is image text generation? You can see from this picture. Basically, it's generating a description about the image. For example, given the image on the left, you have maybe 3 possible descriptions of this image, from simple ones to more detailed ones. And this problem has 3 variations. So from simple to complex, it can be divided into image captioning, dense image captioning, and image paragraph generation. I will cover this one by one. So, first, I will try to look deeper into this problem. So why this task is hard? As you can see from the right picture, if you want to generate a description about this image, you have to consider many things. For example, you have to identify the objects. In this case, is cat and dog, and also you need to know their attributes, such as it is a white cat, and it's also a furry cat. And also you need to understand the relations because these two are playing together. And also you need to understand the location. These are all like very hard for neural models. Maybe in some cases you need some external knowledge to do some reasonings. For example, if you see a birth cake in a picture, you may generate a sentence like who is having the birthday, something like this. This you must this needs some common sense knowledge, not just the information from the picture. So that's the reason why this task is very it's very hard and also interesting. So before moving to the models, I listen here what is a good image caption. The current image caption data sets are labeled by humans. So they have some standards for the annotation. For example, this is the annotation guideline for the Flix data set, I think. Yeah. You can see what are the bad image captions. See the red ones. For example, in the fourth, it says it completely ignores the dog, and in the fifth one and the sixth one are bad and very bad. And the very good one is the first one because it describes the dog and also the hat, and it also describes the relationship between these two. Okay, so I have already mentioned that there are 3 variations of this task. So I will first introduce the first 2 ones. Image captioning is basically generate one sentence, a general description of this image. And the dense captioning is to generate a description for each part or each object inside the image. You can see the difference between these two. And moving from dense captioning to image paragraph generation, you can see it from this picture. So the top one is the dense captioning. You just generate 1, 2, 3, 4, 5 sentences. Each sentence describes one section or one object of this image. But the paragraph, for the paragraph generation, you need to generate a coherent story about this image. So it is much harder than the previous one.
So is that ground truth or is that generated by a model?
This is the ground truth.
Oh.
Of course.
But that doesn't look that hard, does it? I mean, you have to be able to serialize the topics, but sort of each one is a patch of the image that you could describe independently, right?
Yeah, sometimes sometimes you just concatenate these 5 sentences about you can get some reasonable paragraph, but in some cases you need to add some sentences to make the whole story more coherent. Yeah.
Okay.
And there are a couple of image capturing data sets. I think from my understanding, they are similar, except for the size. For example, the pasta only have 1,000 image capturing pairs, and the right one have 2,000, and the Flickr has 8,000. And these data sets are also different in the domains they describe. For example, this one is called abstract scenes, and it contains the image captions based on these cartoons. And other data sets are mostly based on the real scene images. The most famous one is the one on the right. It's called NUS Coco data set. This data set is very large scale. It has over 100,000 K. 100,000 image caption pairs. I also want to mention a data set called this one called Visual Genome. It is a data set developed by Stanford. I will show you their website. Yes, you can see actually what they did is to use a very comprehensive data set which includes almost everything. So you can see. First, they have many images, and for each images, they identify the regions or the objects inside the image, and they also generate a caption for each region. And also, they label the relationships between different regions. This data has actually very rich information. You can see one example here. They have a visualization system, as you can see. These are attributes, and these are relationships, and these are regions. And they even have the question answering pairs labeled by humans. This data set is very popular in image captioning domain. Okay, let's back to the slide. Sorry, the computer is very slow.
It hasn't caught a coronavirus, right?
You said the latest Windows update erased a lot of people's computers.
Huh?
Like the one last week, I think.
Ah.
So you should not update your computer.
Yeah, definitely. Okay, let's continue. So after data sets, I will briefly introduce the models. So here is a general categories of the deep learning-based image captioning models, and it can be categorized based on different standards. For example, supervisor on supervisor, and also encoder-decoder architecture or compositional architecture, or even based on the task. Like I said, is image captioning or dense captioning or paragraph generation. There are 2 common paradigms for image captioning. First one is the encoder-decoder architecture. This one is very standard. You just use an encoder to encode the image and use a decoder to generate the language. And second one is compositional models. It treats this task not end-to-end, but in different stages. For example, for dense image captioning, It usually first identify the regions, and then based on each region, they generate a caption for that region. For first category, very typical one is this. Yeah, it's very simple. It's CNN plus RNN. Just use a CNN to encode the image and then feed the image features to the RNN language decoder and then generate the image caption. I think this is like a toy model. For the dense captioning, there is a model in published in the CVPR 2016. It's also from the same group as the visual genome. It calls a dense cap. This model is like what I said. It is a conversational model. It first localizes all the certain regions of an image and then generate descriptions for those regions one by one. And this model is a recent model used for the image paragraph generation. It's called a hierarchical generation model. So actually the idea is it's also very simple for my understanding. So first they use a CNN to encode the image feature on the left, and then you also use a region detector to extract the region features, and then they feed this image feature and also the region features into a hierarchical RNN. So why they use hierarchical RNN? Because they want to generate a paragraph. So in this case, they must consider the coherence between sentences or the relationship between sentences. So in their model, they first use a sentence level RNN to generate the hidden states for each sentence, and this hidden states is also computed based on the attentions over the regions in the image. So in this case, they can ensure that the sentence states actually focus on different regions in the images, and for each sentence hidden state, they then feed it into a word RNN to generate the actual sentence, as you can see in the left, in the right. Okay, this is a summary. So actually, these models are all incremental models, and their architectures are very similar. They differ in the use of image encoder and language model. As you can see, the most common image encoder is the ResNet and the VGG, and the language model is either RNN or S10. And they also differ in some tricks or techniques that I showed on the right. For example, some use attention and some are not.
How come there are no newer papers?
Sorry?
There are no 2018 and before.
Yeah, because this survey paper is written in 2019. Yeah.
No one is using a transformer decoder.
They are now.
Yeah, they are now. Yeah. So for the evaluation, these 5 evaluation metrics are most common. So blue, rouge, and medials. These 3 are common LG metrics based on the n-gram matching. And the first one is called CIDR. This one is to measure the diversity between different sentences. And the last one called SPICE. This one is specially designed for image caption evaluation. And actually, I don't know too much details about this one. Yeah, that's a picture. Okay. Okay, this is the last slide. For the evaluation, I have seen one paper I think is very interesting. As you know, evaluation metrics is a very important problem in natural language generation because So most analogy papers still use human evaluations because they think that humans is the most reliable. Actually, in this paper, they actually calculates the correlations between the human judgment and the automatic evaluation metrics. As you can see, they have tried the blue meteor root and the cider. And you can see the figure. This means that, for example, when blue is very low, then it is very high. Then it is in a very high probability that the human also think that the caption is bad. Yeah, and when blue is high, and is less likely that a human will think this is bad. So if actually in this figure we can see that actually all these four evaluation metrics correlates quite well with human judgment.
But only on the bad side, right? So they all correlate
Yeah.
to say that your image is crap or your caption is crap, but you can't tell whether the captions are good, right?
Yes, right. Yeah, you can see that the left part is very high. This means that when the blue thinks that the image caption is bad, the human also thinks it is very bad, but not on the opposite direction. When blue thinks it is very good, human does not necessarily think that it is also very good. Yeah, that's all. I think so. Only 20 minutes.
Actually, I wonder if there's a way to put together maybe OpenAI's GPT-2 with some sort of image encoder like VGG or ResNet and come out with better results.
Yeah, sure. I think maybe someone already tried this because this is the easiest way to think about it. Yeah. Actually, in general, I think the most innovations in image captions are more focused on the image side, or more focused on the computer vision side, not on the language generation side. Actually, I think many researchers in computer vision still think that bird is very novel. So I think that is why in the papers that I list, no one has ever used a transformer for the decoder.
That's what I'm trying to do for my project.
It's very noble, you say.
Novel, very novel.
Basic bird is very noble.
Noble.
Well, I didn't say the graph. The lower value is bad, is good or bad.
Sorry?
Like when you look at when it's closer to
That means
zero,
no
it's
correlation.
there's a correlation with the blue.
So
Yeah.
the score goes from on the x-axis, right?
Yeah.
So 0 to 100 for blue, 0 to 100 for
Yeah.
blue. And then the correlation value is on the y-axis.
Yeah.
Right. So you're saying when all the left-hand peaks are saying that all of the metrics agree that when things are bad, they're bad.
Oh, okay. So when it's close to zero, then it's bad.
Yeah.
Okay.
Some of them on the right-hand side can tell you that things are good, right? But not that much correlation. I mean, ideally, all of them would point to the same thing, right? Humans should point to each other. But I think, yeah, there's a lot of problems with this. It would be interesting to correlate drunk humans with sober humans and see how well they correlate. I think, certainly people with impairments or creative thinking as induced by other medicine might give you very different values for their caption. Okay, let's thank Liangming and everyone for this. Next week is recess week. We still have class. Heng Chan and Taka will be going.